Software timing control falls into two categories. The first is execution timing, which temporarily halts program execution to free the processor for other tasks, typically managed by wait functions. The second is software control timing, which ensures real-world actions occur within a specified time frame and regulates loop execution frequency through software polling. For instance, when collecting data, maintaining consistent intervals between samples is critical. This is where software control timing is essential. It checks the system clock to confirm whether the set interval has elapsed. These differences clearly distinguish execution timing from software control timing. This is another example of execution timing. This is a producer-consumer design pattern. In the producer group, there is an event structure, and this event structure has a timeout terminal. If it is not wired, then the event structure will wait indefinitely until the event happens. Similarly, in the consumer loop, it uses the queue to get the data from the producer loop. And there is also a timeout setting for this to-queue operation. If it is not wired, then the timeout will also be indefinite. This is another example of execution timing using a producer-consumer pattern. In the producer loop, the event structure is configured with a 100 millisecond timeout. Likewise, the consumer loop sets a 50 millisecond timeout for the to-queue operation. This example demonstrates both execution and software timing. The delay function is configured for a 5 millisecond pause, representing execution timing. The delay timer starts alongside the loop's code execution. If the code finishes in less than 5 milliseconds, the CPU is freed for other tasks and resumes after the delay period. If the code takes longer than 5 milliseconds, the delay has no effect because it expires before the code completes. The elapsed time express VI handles software timing by checking whether a specified time interval has passed. Here are two key delay functions for execution timing. The first is the wait function, which pauses execution for a specified duration. For example, wiring the value 100 will cause the program to wait for 100 milliseconds. The second function, wait until next millisecond multiple, works differently. When you provide a value, say 100, it aligns the wait with the system timer, which counts milliseconds from a reference point. The function times out when the timer reaches the next multiple of the input value. This approach is useful for synchronizing multiple loops because the timing is based on the system clock rather than arbitrary delays. There are three timestamp functions. The first is the tick count function, which returns a millisecond timer value based on a predefined reference point. The second is high-resolution relative seconds, which works similarly to tick count, but provides a double precision value with microsecond accuracy for higher precision. The third function is get date and time in seconds, which outputs the current date and time, including year, month, day, hour, minutes, and seconds. This example demonstrates how to use the date and time in seconds function. First, the function retrieves the current time, which serves as a reference and is stored in a shift register. During the acquisition phase, the current time is obtained again to calculate the time difference. If this difference exceeds the specified wait time, the comparison returns true, prompting the code to switch to the analyzer phase. At that point, the new current time replaces the previous reference time.